SwayamPrabha. Digital India. Educated India.
Hello and welcome to lecture 53. We are discussing about transonic compressors. In last lecture we started discussing about the effect of different flow parameters on flow behavior within the blade passage. We were discussing about the formation of losses. We have discussed about the different losses, that's what is going to occur because of change of incidence angle. Then we were discussing about the effect of change of area ratio. We were discussing about the effect of change of pitch to chord ratio. As we have discussed, now we are more interested towards the development of these aerofoils. So today's lecture, that's what is mostly covering the part, that's what we say, how to develop these transonic aerofoils. Now in order to have detailed understanding for the development, we need to have some fundamentals of geometry, trigonometry, as well as some mathematics what you have already studied during class 10 or 12. Let's move ahead with. So here this is what we are discussing in sense of development of camber line. So if you recall, this is what we were discussing when we have discussed about subsonic aerofoils, or when we were discussing about subsonic compressors design, where we have discussed about the different types of camber lines. We have said like circular arc camber line, parabolic camber line, polynomial camber line, exponential camber line, DCA camber line, MCA camber line. Now if you look at this circular and parabolic camber line, that's what is mainly been used for subsonic aerofoils. Even double circular arc also people they started using, that also we have discussed. Now for transonic and supersonic aerofoils, we are looking for different kind of camber shapes or camber line shape. They are polynomial type or exponential type, DCA type or MCA type. So let's try to learn how exactly we will be making these camber lines. We are discussing about development of the camber line for the transonic aerofoil. So we can say what line we will be developing, that line need to be a smooth line. When we say we are looking for smooth line, that's what will be having number of points, that's what is set nearby. Secondly, we need to decide the formulation or the equation for that camber line, and that camber line equation need to be such that it will give if you give certain boundary conditions, maybe at the leading edge or maybe somewhere in the mid chord or maybe in the trailing edge region, then it should give the solution for that. If we consider, we can represent any camber line equation as y is equal to function of x, where x we can consider mainly people they are considering x as chord length, but the sake of brevity here in this case we are considering x as location rather than defining that as a chord, because that's what will be helping us in solving the equations. So in case of solution of the equation, what all we are discussing, those equations are quadratic equations. Now those equations, when we say we need to solve that equation, for solving that equation we are looking for different kind of boundary conditions. So if you recall, when we were discussing about subsonic aerofoils, that time we have discussed the first condition, that's what is all points that need to be fit on the line for particular coordinate system. If you recall, we were discussing about the slope at the leading edge, and third boundary condition we were discussing, that's what is say slope at the trailing edge. Now this three boundary condition, that's what is sufficient when we are discussing about say circular arc camber line. We are discussing about the transonic aerofoils development. Under that condition we are looking for some special conditions. If you look at here, say many supersonic aerofoil, that's what is required little cambered near the leading edge. This cambered, it may be 0 or it may be negative or it may be positive. Now in order to have that cambered, in that case we are looking for some boundary condition. That boundary condition we can say second derivative of the camber line at the leading edge. How to get that? Say in order to achieve that second derivative part, the ratio between the second derivative at the leading edge and point where the absolute value of second derivative is maximum, that's what we will be considering as a boundary condition. So this is what will be my fourth boundary condition. Now similar to that we will be having trailing edge, and for trailing edge also we need to have the boundary condition, because we can understand when the flow, that's what is flowing from my suction surface and the pressure surface, near the trailing edge we will be having the flow, that's what will be subjected to some deviation angle. And if we will not take care of the curvature at the trailing edge, it may be possible that we will be having rise of losses. We define that as a wake loss or the profile loss. So for that also we need to put the fifth boundary condition. So we can say these boundary conditions as say at x equal to 0, y equal to 0, that is nothing but at the leading edge my first derivative I will be putting as a tan alpha 1. This alpha 1 is nothing but my inlet flow angle, and y double dot, that's what is a second derivative, we can say it is p, that's what is some constant, into second derivative, that's what is having maximum value. At x equal to L, we can say this is what is at the trailing edge, we can say y dot, that's what is say my first derivative, that's what we are writing as a tan alpha 2, and second derivative we are putting q into this second derivative which is having maximum value. Now this is what is more in sense of mathematics. Let's try to understand when we will be discussing the development of different kind of camber lines, that's what will be giving more clarity. Now very first let's try to develop say polynomial camber line. So here in this case, say this is what is a kind of camber line what we are looking for. Say this is what is say my assumed camber line, which is having say inflow angle we can say is alpha 1, my outlet flow angle, that's what is say alpha 2, we can say this is what is say my chord length C, this is my axial chord, and this is what is representing B, that's what we can say some kind of location, say we can say it's a function of x equal to L. Now in order to develop this polynomial camber line, we need to select some equation. Now there is a good literature, that's what is available, that's what was very old literature, but still that's what is giving very good understanding and explanation for the development of such kind of camber lines. So here what all we are discussing, that's what will be giving you some idea. Later on, as per your expectation or as per your requirement, you can modify the formulation of this line. Say here we are assuming our polynomial camber line equation as say x minus h square equal to say 4a y second derivative minus k. That's what we can say, it's a parabolic equation. Now this is what is my second derivative. If I will be simplifying that, this is what will be giving me the equation in sense of y equal to f of x. Here in this case, h is nothing but the position on the x axis where the second derivative, that's what is maximum. That is what is of our interest. K is the value which the second derivative has at that point, and A, B, C, H and K, they all are the constants. Now in order to get the solution for this equation, we need to find this constant, say what constants we are looking at, that's what is say A, B, C, H and K. Those all constants we can achieve by putting different boundary conditions. So we are putting very first boundary condition, we can say at y equal to 0 and x equal to 0, we will be getting the value of some constant C. Same way, if we are considering our boundary condition at say leading edge, what we have defined at say x equal to 0, my first derivative, that's what is equal to tan alpha 1. So that's what is giving me the value of constant B. Now what we know, as we have discussed, for many say aerofoils, we need to have slight camber, that's what need to be provided at the leading edge. In order to have that as a configuration, we are putting our boundary condition as we have discussed. This is what is at x equal to 0, my second derivative, that's what I am writing as P into say second derivative which is having maximum value, that's what will lead to give me the value of K as well as the value of P. Now we know what is the slope at our trailing edge. Based on that, we can calculate what will be the value of A. So here in this case, we will see we are having say constants, we are calculating A, B, C and K. Now as we have discussed, we are also looking for say trailing edge configuration. We need to take care of what is happening with our say deviation angle. In order to have that in line to what we have done at the leading edge, we will be doing say putting boundary condition as say leading edge what we have done. So here in this case at x equal to L, my second derivative I am writing as some value of Q into second derivative which is having maximum value, that's what will lead to give me the constant H. Now you know we are having 5 constants and we are having say different equations. We can say L square plus B square plus C is equal to C square, that's what is based on my trigonometry. And here in this case at x equal to L and B, if I will be putting those numbers, we will be getting the value of this B. Now what all we know all these constants. Now for particular value of x, we can calculate what will be the value of y, and that's how we will be generating the coordinates, say x coordinates and y coordinates. So you know, like in order to have the development of our pressure surface as well as say for suction surface in line to this, for camber line, here in this case this camber line, that's what can be developed by using this particular equation. Now let's see what all input parameters we are looking for in order to develop this camber line. Suppose say we are looking for polynomial camber line, we are looking for data as a stagger angle, we are looking for say length, we are looking for say maximum thickness in sense of percentage chord, leading edge radius, trailing edge radius, maximum thickness to chord ratio. We will be looking at number of points to be developed for each. Okay, we are looking for say leading edge angle, that's what is alpha 1, trailing edge angle. We are also looking for say normalized curvature of camber line at the leading edge, that's what we say as P, that's what is in the range of 0 to 1. Same way normalized curvature of camber line at the trailing edge, that's what we say as Q. Conventionally it says like Q, that's what is having say value in the range of 0.5. For most of the application, we are not considering say we will be having say camber or say slight camber at the leading edge, and that's the reason why P equal to 0, that's what is quite satisfactory. Towards the hub region, when we are developing the camber line for say hub region, where we need to have P value to be slightly smaller, or say that's what is a positive value we need to consider. Near the tip region, we need to consider this P value to be negative. So this is what will give us idea how do we develop say polynomial camber line. I'm sure this is what will give you idea how exactly we will be developing this line. Now, in order to develop this kind of camber line, you need to write the program. Say, suppose if I consider I am having blade, for that blade I will be having number of stations, and for all those stations we are looking for the camber line. And based on my alpha 1 and alpha 2, if I will be putting these numbers, taking care of all this, what all we have discussed, we will be able to develop say polynomial kind of say camber line. Now, second camber line, that's what we say is an exponential kind of camber line. Now, what is happening here is for say polynomial kind of camber line, we are not having much control in sense of formation of say curve for specially camber line. Suppose say I want to develop multiple circular arc kind of configuration or multiple circular arc kind of aerofoil. Under that condition, we need to put some extra location here. So this is what we can say, this is what is a location at say some point S, we say that as say inflation point, and this is what is some angle alpha S. So what we will be doing, we will be putting some point, that point we will be having control on that. So we will be having say one line up to some location, we will be having second line up to some location, and that's how we can go with the development of this kind of say camber line. So here in this case we will be using two different equations. As I discussed, we will be having say one equation of camber line up to this inflation point. We will be having second camber line equation, that's what is from say inflation point to the trailing edge. So let's consider say exponential kind of equation. So this is what is the equation what we are considering, say second derivative of y, that's what is equal to b into bracket x minus s e to the power a x minus s. Okay. Now suppose if we consider, as we are discussing, we are considering the location from my leading edge to some inflation point, this equation we can write down say as y1. We will be having some constants a1, b1, c1 and d1, and L, as we have discussed, it's an axial chord, and this is what is a function of say x equal to L. Now in order to solve this, we need to put certain boundary conditions as we have discussed. This boundary conditions, that's what will be remain similar to what all we have discussed in earlier case. We are looking for 5 boundary conditions. First, that's what we have discussed is y1 equal to 0 at x equal to 0, that's what will be giving me constant d1. When I am taking say x equal to 0, this is nothing but this is what is my slope as we have discussed, that's what will be giving me my second constant as say c1. You can do pen paper calculation in order to check with what all numbers we are putting here. Now as we have discussed, near this leading edge we may need to look for say slight camber, and that's the reason why we are incorporating this boundary condition where we can calculate what will be the value of say constant p. Same way, now we are reaching at location x equal to s. So in previous case for polynomial camber line, what we have done, that's what is say at leading edge and trailing edge we have given the boundary condition. Here in this case we will be putting this boundary condition at say inflation point. So this is what we are putting at the inflation point. Now if we look at say we are having two values of constant c1, one that's what we have received by considering x equal to 0 and slope factor, and this is what is say my second boundary condition. So based on that, if we are solving, we will be getting the constant b1. Now let's move towards the next location. So this is what is my next location. So my equation, that's what will be written as say y2. We can say this is what all are the constants a2, b2, c2 and d2. Again we will be putting our boundary condition at say inflation point. So at x equal to s, we will be having y2 dash equal to 10 alpha s. That's what will be giving me my constant c2. Now when we are putting this location, this particular location, we need to be very careful what point we are discussing about S, that need to be a smooth point. So like the line what we are drawing, that line need to be smooth at this connection point, and that's what we are putting here at x equal to S, we are putting y1 equal to y2, and that's what will be giving me second constant as a d2. Now we will be putting say next boundary condition at x equal to L near the trailing edge. That's what will lead to give me say second value of C2. Again, if we will be solving these two values of constant C2, we will be able to achieve the value of constant B2. And same boundary condition, in order to consider your deviation angle configuration, we will be putting the boundary condition of second derivative and its maximum value. That's what will lead to give me the value of Q. We know what is my L square plus B square, that's what is cot square, and at x equal to L and y equal to B, that's what will be giving me the value of B. Now all these parameters, that's what will be helpful to us in order to develop the exponential camber line. So let's look at this exponential camber line. Now as we were discussing, we are having say different values of P and Q. In order to have say special requirement at the inflation point, we need to be little careful of, and it says we need to have our A1 value, that's what is my constant value A1 and constant value of A2, that need to be selected in this particular range, because we can say I will be making my curve here, I can make my second curve here, but when we are having this connection, it should not have any jump, it should be smooth one, and that's what is very important, and that's what we can consider by providing particular boundary condition and selecting these numbers. Okay. Now suppose say if we are looking for development of say exponential camber line, again what all we are looking for is say our stagger angle, we are looking for the length of the chord, location of the maximum thickness, leading edge radius, trailing edge radius, maximum thickness to chord ratio, we are looking for say leading edge angle, that's what is say alpha 1, we are looking for alpha 2. Same way here we are looking for say constant value of P and Q. Two additional points we need to care for here, that's what is the location point of inflation in percentage chord. So we are looking for where exactly we want to put our inflation point. Are we looking for this inflation point towards the leading edge? Are we looking for say this inflation towards the trailing point? At what location? That's what is very important, and that's what we are defining in sense of percentage chord. At the same time, we are also interested in putting the inclination. Okay, at what inclination we are putting this line, that will make the shape of my aerofoil. So if you recall, when we were discussing about the multiple circular arc aerofoil, we are having say different kind of configuration where we may be required for managing our flow towards the trailing edge. Okay. Now double circular arc aerofoil or say double circular arc camber line, what we are looking for, that's what can be represented in sense of this equation, x minus x0 square minus y0 square equal to r square, and based on that, if we will be putting our boundary conditions, the same boundary condition what all we have discussed in sense of condition 1, condition 2 and say this condition 3, based on that, and we will be having our Pythagoras law, we will be able to achieve what all we are looking for in sense of coordinates for my camber line. So this is what is for double circular arc camber line. Now there are different methods, people they are opting with different kinds of double circular arc camber line. This is what is one of the method. One more method, that's what has been discussed, we will see. Now in order to develop this double circular arc camber line, here in this case this is what is straightforward with we are having say 3 boundary condition, that's what is sufficient for us, and based on that we can say we can put our stagger angle, we can put where we will be having maximum say thickness, we know that's what is at the 50% of my chord, what will be my leading edge radius, trailing edge radius, and you know what will be my angles alpha 1 and alpha 2. That's what will be sufficient condition for development of double circular arc camber line. Now, as I was discussing, this is what has been discussed by Ongier in his book. This is also for the development of double circular arc aerofoil, rather defining in sense of double circular arc camber line. So, what they have done here in this case, we will be having maximum thickness, that's what is been placed at the 50% of chord, and upper surface and lower surface coordinates, that what is has been kept with. This is what is representing the upper radius, this is what is representing the lower radius, we can say pressure surface as well as the suction surface, and this is what is for say my camber line equation. So, my coordinates delta x, that's what we can calculate based on trigonometric rule. Delta y for upper surface also can be calculated based on the trigonometry. Now, this theta, that is nothing but which is representing my camber angle. Now, in order to achieve this curvature or say radius of my upper surface, we need to go with the number of iterations solving this upper surface and lower surface, and that's what will lead to give the radius of my upper surface, that's what is as a function of this d, what is my r0, that is nothing but my radius at the leading edge, what is my chord, what will be my camber line or camber angle. So, this is how we can achieve our upper surface or upper radius. In line to that, we can achieve what will be our lower radius. So, this is also one of the method. Other people, they are developing the double circular arc aerofoil with some different approach or different methodology. So, here in this case, this is what is representing double circular arc kind of camber line. Now, let us move with what all we are more interested in or say for future development of our transonic aerofoil, that's what is say multiple circular arc. We can say that's what is of S kind of shape. So, in line to what all we have discussed for our exponential kind of say camber line, we will be using the similar kind of logic, but here this is what is been developed in a different way. So, here in this case also we are looking for say inflation point. So, this is what is my location for inflation point, and this is what is my inflation angle. Now, up to from leading edge to my inflation location, we will be considering one curve, one line, or we can say one camber line, and from say inflation point to trailing edge we will be considering other line. Okay. Now, there are different methodologies, different authors, different researchers, different companies, different universities, they are developing their own camber lines for multiple circular arc. Here in this case, for the sake of simplicity, what we have done, say up to our inflation point, we have considered this as a straight line. So, here this equation we can say that's what is given by y1 equal to tan alpha 1 into x. We can say this is what is the equation of straight line. Now, in order to have the other line, say this is what is from inflation point towards the trailing edge, that's what we can consider as a circular arc. So, this is what is x minus x0 square minus plus y minus y0 square equal to say r square. Now, in line to what all boundary conditions what we have discussed, we will be putting those boundary conditions here. So, here in this case, if we are putting our boundary condition, that's what will lead to give us all the variables, all the constants. Now, once we have derived with the constants, we will be calculating our x and y coordinate for the camber line. Okay. Now, in order to develop this multiple circular arc camber line, additional parameter what we are looking for is a location from where the arc that will be started with. So as I told, like for development of multiple circular arc aerofoil, many people they are considering two circular arcs, say initial circular arc, second circular arc, and based on that they are developing their multiple circular arc camber line. This is one of the method whatever we have discussed. We will be having straight line, that's what will be followed by the curvature, or we can say that will be followed by circular camber line. So as per how we want to manage our flow on the suction surface of our blade, we need to modify or we need to make the aerofoil, or we need to make our camber line. So once we are ready with our camber line, very next question that's what will be coming is how do we put our thickness. So let's move towards say having the distribution of the thickness. So for transonic aerofoils, say especially when we are considering the thickness distribution, that's what is been defined in sense of say polynomial, say third order polynomial. So here we are considering, suppose if we are considering the location somewhere up to somewhere some location, we can say that's what is say my maximum thickness location. We can say this is what is my Z location. So it says in between 0 to Z, or say from leading edge to some location, we can say we will be selecting third order polynomial thickness distribution. That's what is say A into x cube plus b x square plus c x plus d, where A, B, C, D they all are the constants. And as we know, in order to solve these equations and in order to get this constant, we need to put different boundary conditions. So these boundary conditions are say at x equal to 0, we will be putting say second derivative of this equation to be 0, and that's what will be giving constant b. At x equal to z and y1 we will be putting our leading edge, we will be having d equal to y0. Same way at x equal to z and t, this capital T, that's what we are defining in sense of thickness to chord ratio. Okay, and this is what is my third boundary condition. In line to that we will be putting our fourth boundary condition, and by putting these boundary conditions we will be able to achieve what are the constant A, B, C, D for this equation. Now as we know, this is what we are saying as a axial location. It is not the chord. This is what is my axial location. So we will be selecting different x values, and for those x values, by having this constant, we will be able to achieve the y values. Okay, so that's how we will be calculating our thickness distribution on suction surface. We will be able to calculate the thickness distribution on our pressure surface, especially up to some location Z. Now, later part, say towards the trailing edge, there also we are taking say third order polynomial, but we know in that particular region we are looking for the management of shock in a different way. So third order polynomial equation, that's what is been defined in a different way. So this is what is the equation, that's what people they have defined with. As I told, there is nothing that's what is fixed. You can use your own equation based on your requirement. Maybe based on your computational study, you can modify this distribution. Okay, so this is what is representing how my value of y, that's what is varying with the x. We will be putting different boundary conditions at z, and this is what is at say my trailing edge location. We will be able to achieve the distribution of the thickness on say suction surface as well as on the pressure surface towards the trailing edge side. Okay, now in order to avoid the inflation point on the blade surface, it says we need to take care of this number. So z minus f divided by 3e, that need to be larger. We can understand when we are discussing, we are selecting say multiple circular arc. For that multiple circular arc, we are having the inflation point, we have inflation angle, and when we are doing our distribution of the thickness for suction surface as well as for the pressure surface, it should give the smooth curve, and that's what is need to be managed. any jump or any sharp edge, that's what is not been allowed or permitted when we are discussing say transonic kind of aerofoils, or when we have a flow, that's what is say supersonic flow. Okay. Now some of the literature, it says you can go with say circular thickness distribution also. So we can say we will be going with say circular arc thickness, that's what is given by x minus x, and this is what is y. So in order to avoid the confusion, there is nothing at x suffix 10, it is just for segregating from other constants. Okay, and we can use this circular arc thickness distribution up to some location, as we have discussed. By providing different boundary condition, we will be able to achieve different constants. When we derive the constants, we will be getting say values of x as well as y. Now this is what all we are discussing. That's what is very hectic process when we are doing pen paper calculation. So it is advised that you just learn some coding tools, maybe by using say your C, C++ or MATLAB. Using those say program language, you can develop your own code. You can develop your coordinates x and y for say suction surface. You can develop your coordinates for x and y for say your pressure surface. Even you can develop your own camber line. You can play with the equations, and that's what will be giving you what all we are looking for. As I told, there is no superficial rule for having say thickness distribution to be followed by this equation only. Okay, as per the expectation, what all you are getting, if it is serving your purpose, your expectation, your required result, that's what is your aerofoil. So maybe it may be possible that you will be going through the development of aerofoil. You can name that aerofoil as your own name. Yes, this is what is possible. So whole lot of scope, that's what is been lie in sense of development of these aerofoils. So people initially they are going with say computational study. Using CFD they are developing this kind of aerofoils. Later on, in order to build the confidence, they will be doing say cascade testing, you know better now. Based on those cascade testings, they will be having performance map, and that performance map, that's what will be used for the future development of blades. Now towards the trailing edge also, you can use the same circular arc thickness distribution. Similarly, you will be getting your x and y coordinates, and this is how you can have the distribution of thickness for transonic aerofoils. With this all understanding, let's take the case for the development of say cascade. Now let's take some of the cascade parameters. Say we are assuming say chord length as say 8.6 centimeter, solidity as say 2, turning angle 48.4 degree, stagger angle 16 degree, maximum thickness as 20% of chord, maximum thickness value is 7.4% of the chord, leading edge radius we can say is 0.04 centimeter, value of P is 0.25, trailing edge radius is 0.02 centimeter, Q value is say 0.5. The location of the inflation point, that's what is at the 60% of the chord. The inclination at the point, it is say inflation angle we can say is a 70 degree, as where it is applicable. The thickness distribution we can say the circular arc thickness distribution. We will be considering our inlet Mach number to be 0.7. So with this all input data, let's try to generate the aerofoils, what all we have learned. So here in this case, if we will be putting all those input parameters, this is what is representing different kind of say camber lines with say thickness distribution. So here this is what is representing my polynomial kind of camber line. This is what is representing say exponential camber line. This is what is a 70%. location, we say it's a inflation point, it is placed 70%, and my alpha s, that's what is angle, we are putting 30 degree. Suppose if we are putting that as a 40 degree, you can see the variation of the shape of this aerofoil. You can clearly see the difference between these two. Same way, if we are considering say double circular arc kind of configuration, this is what is double circular arc configuration. Now when we are considering say multiple circular arc, as we have discussed, this is what is my straight line. We can say my point, that's what is placed at say 45% of my chord. So this is what is representing my second circular camber line. Okay, and this is what is the same circular distribution of my thickness. This is what is with when we are having say my inflation point, that's what is been placed at the 60% of my chord. So we can see the clear difference, clear variation. That's what is happening by changing the position of my inflation point for say multiple circular arc camber line. Now here in this case, this is what is a representation of different camber lines. So we can say this red one, that's what is representing my polynomial camber line with all inputs what we have discussed. We will be having say exponential. Here in this case for the exponential, when we are having our alpha s, that's what is inflation angle, that's what is 30 degree and 40 degree, we will be having clear variation. That's what is happening upstream condition. Just look at even towards the downstream condition also. So the location of this inflation point, that's what is very important. We need to be very careful about that point. This is what is representing my say double circular arc. Same way for say this black color, that's what is representing multiple circular arc. And this is what is representing how my camber line for the same thickness distribution, how the blades or the aerofoils they are being generated with. Now with this we can say we are able to generate the aerofoils, and after generating this aerofoil we will be managing our flow passage, and by managing our flow passage basically we are managing our shock structure. We are managing the placement of our normal shock, and that's how we are managing our diffusion within the flow passage, and that's what will be helping us for development of future more efficient aerofoils. So this is what will give some feeling of special kind of application with different kind of camber lines and circular arc thickness distribution. Now in next week we will be discussing about how do we design those transonic compressors. Thank you very much for your kind attention, and I am sure this is what all will be giving you some different kind of feeling with say development of transonic aerofoils and transonic compressors. Thank you very much.